Hello, this is Charlotte coming to you from a very hot and sunny Pretoria this morning. We are going to look today at the neuromuscular junction, and we're going to tie that in with our muscle relaxants, and we're going to look briefly at what happens with malignant hyperthermia. So this will be very helpful for medical students and for people preparing for the DA or even for the FCA Part 1 exam. Okay, so let's start off by just drawing our neuromuscular junction. So first we have our nerve axon and we have our muscle end plate. And of course the muscle end plate is continuous with the sarcolemma or the cell membrane for the muscle cell. And your sarcolemma makes these so-called T-tubules, called that way because it looks like a T. Easy, right. But this is now the muscle end plate. Right. Now, what happens when we get a nerve stimulation is that we get opening of so-called voltage-gated calcium channels. And they're called that way because when you reach a particular voltage, they will open. And what will happen then? They will allow calcium to come into the cell. And the calcium has a very particular job. It helps to get these deep vesicles to move more superficially to release acetylcholine. These little green dots is our acetylcholine, to release them into the neuromuscular junction. And what does the acetylcholine do? Acetylcholine then goes and binds to the nicotinic receptor. Now remember that your nicotinic receptor is basically a little pore, a little channel, and when acetylcholine comes and binds to it, it allows, just close that again, it allows sodium to rush into the cell. So it's like a little pore that allows sodium to go into the cell. Now we must also remember that our cells have a resting membrane potential, right? And that is usually for muscle cells around minus 90 millivolt. So when the muscle is resting and nothing is happening, that is where your resting membrane potential is at. But now if I'm bringing a lot of sodium into the cell, sodium has a positive charge, right? So what's going to happen to our resting membrane potential? It's going to become less negative. And when that reaches a particular threshold of minus 50 millivolts, more or less, we're going to see other sodium channels opening up. And suddenly we have a much larger influx of sodium into the cell, more positive charges coming in. So we're going to get a sudden increase in our resting membrane potential, and this is called depolarization. Why is it called that? So if you think about North Pole, South Pole, or in fact positive pole and negative pole, your resting membrane potential is at the negative pole. When we now bring a lot of positive charges in, it becomes less negative. We are moving away from the pole. We are depolarizing, right? And that will continue until we reach about plus 30 millivolt, at which point these sodium channels close down, and we're then going to get a slow leak of potassium out of the cell from some other channels. So potassium leaves, so now you have positive charges leaving. You're becoming more negative. You are repolarizing. Your repolarization will always overshoot a little bit before it goes back to baseline of minus 90. And we have very special channels here that we've all heard about. It's your sodium, potassium, ATPase pumps. And they use energy to pump sodium out of the cell again and potassium back in where it belongs, and that then restores your resting membrane potential. Incidentally, the thyroid hormone increases your metabolism by increasing the number of sodium, potassium, ATPase pumps that are expressed because it uses energy. So that's one way to increase your basal metabolic rate. I find that quite interesting. Okay. So we've had this wave of depolarization, okay? And this wave of depolarization is going to spread all the way along from the muscle end plate, along the sarcolemma, and down your T-tubule. And what's going to happen then is that you actually have more voltage-gated calcium channels along the sarcolemma, and they're going to allow calcium to come in, and they're going to bind, or they're going to send a message to something called the Ryanodine Receptor. Now, I'm just going to call him Ryan. We're going to come back to Ryan a bit later. So in this little picture, Ryan is a very friendly little receptor. And what happens when calcium knocks on Ryan's door, the calcium tells Ryan, Ryan, we want our friends to come out and play. Now, Ryan, the Ryanodine receptor, sits on something called the Sarcoplasmic Reticulum, or the Endoplasmic Reticulum, just in the sarcomere, in the muscle, right? And basically what the Sarcoplasmic Reticulum is, it's a big bag full of calcium. So there's a lot of calcium in this bag. So these little calciums that have now come in are calling Ryan and telling him that they want the other calciums to come out to play. And Ryan says that is not a problem, and he opens the door and the calciums go out to play. And this is important. So we've had the excitation bit of our excitation-contraction coupling. Now we're going to get to the actual contraction. Right. Now inside our muscle, we've got lots of muscle fibers, right? Lots of muscle fibers. And if we zoom in on this, what we're actually going to see, let's make a bit of space here, is our actin and myosin fibers. So if you think back to physiology, way back, right? It's very wonky, but anyway, you'll get the idea. So we've got actin, which is the thin fibers, actin, actin, and myosin, muscle, it's thick fibers. And actin is like a little skinny Juliet, and myosin is like a muscular Romeo. And all they really want to do is they want to kiss. But there's a problem. There is a bodyguard in the way, and that bodyguard is called tropomyosin. But the bodyguard can be bribed, because the bodyguard has something on it called troponin. And troponin really likes calcium. So all these calciums that came out of the sarcoplasmic reticulum go and bind to the troponin C on the tropomyosin. And whenever something binds to a protein, it changes shape. And all of a sudden, the tropomyosin, the bodyguard, moves out of the way, and actin and myosin can kiss happily. So we get that binding of myosin to the actin binding site. And ATP is released, and you get that power stroke, shortening of your sarcomere, and you get muscle contraction. Okay. But of course, we don't want continuous muscle contraction. We want to be able to have coordinated movement, and for that we need to have contraction and relaxation. So at a certain point, the calciums that were binding so happily to the troponin C on tropomyosin have to go back into the sarcoplasmic reticulum. So Ryan, the friendly Ryanodine receptor, calls all the calciums back again, and they come back inside, and as the concentration decreases here, tropomyosin goes back into its bodyguard shape, and it prevents actin and myosin from binding and from contracting. Okay, so that is good old excitation-contraction coupling. Of course, we also know that in the neuromuscular junction, in our muscle end plate here, there's an enzyme called acetylcholine esterase. And acetylcholine will only bind for a couple of milliseconds before acetylcholine esterase is there to break it down and to break it back into its constituent parts, and then it can be recycled. Okay, so but there's the next lot of acetylcholine being released, and so this whole excitation contraction coupling sequence happens over and over and over again, and that is how we get coordinated movement. All right, so that's the basic function of the neuromuscular junction. I hope that's nice and clear. Now, what happens with muscle relaxants? How does that change the picture? So we still have our neuromuscular junction, and we have our little T tubule. But now, instead of acetylcholine, which is just a single little green dot, we have succinylcholine. Now, succinylcholine, or also called scoline or succinylcholine, however you want to call it, Sux for short, is basically two molecules of acetylcholine joined together. So if we think of our receptor like a little lock, and we think of our succinylcholine as a key, because this key looks a lot like the acetylcholine key that actually fits in the lock, succinylcholine or succinylcholine will bind to the nicotinic receptor, and it's exactly the same lock, so it's exactly the same key, so it's going to unlock the door, and it's going to open the pore, and it's going to allow sodium to come in. So, hey ho, what's going to happen? You're going to go from a resting membrane potential of minus 90 millivolts to minus 50 millivolts, and then you're going to open your other sodium channels, and they're going to come in, and you're going to get depolarization. Exactly the same as what we had with acetylcholine. The only difference is that because Sux is a double key, if you will, it gets stuck in that lock. So now the door can't close again. So this little pore stays open, and you get a continuous leak of sodium coming in, which means that you don't really repolarize, okay? And if you can't repolarize, if you don't reach your resting membrane potential, you can't depolarize again. So this is why succinylcholine causes muscle paralysis. But it's also why it's called a depolarizing muscle relaxant, because you do actually get depolarization. And we see this depolarization as the small fasciculations that the patient gets. Right. But because you don't repolarize, you can't depolarize again, and that's why the muscle is paralyzed. Of course, our lovely acetylcholine that was breaking down, acetylcholine esterase that was breaking down acetylcholine, does not work on succinylcholine. So succinylcholine cannot be broken down by acetylcholine esterase. It is instead broken down by plasmacholine esterase, but that needs to come from far away. It's not immediately in the neuromuscular junction, and that's why your succinylcholine lasts longer than acetylcholine. Sux can last for 5 to 10 minutes depending on what the scenario is, or even more if you have something called scoline apnea, because remember, we can't reverse succinylcholine. Only the body can reverse it with plasmacholine esterase. So if your body doesn't make plasmacholine esterase, you are going to have scoline apnea or succinylcholine apnea, where succinylcholine works for a lot longer than what it would in somebody who has a normal plasmacholine esterase enzyme. Okay. So what about our non-depolarizing muscle relaxants? How do they work? So let's draw them as a little star. So they've still got the basic shape almost like acetylcholine. And these are things like rocuronium and vecuronium and atracurium and cis-atracurium. All right. So it's got the basic shape. So the key will fit into the lock. But unfortunately, because it's not exactly the same, it won't turn in the lock. So if we draw our little lock there, and we draw our rocuronium or vecuronium up there, our non-depolarizing muscle relaxant, it gets stuck in that lock. It goes in, but it won't turn. Your key won't turn in the lock. In other words, the door stays closed. Your little pore stays closed. Nothing can get through. Okay. Hence why it's called a non-depolarizing muscle relaxant, because you cannot depolarize. You just remain at the resting membrane potential until such time as it is metabolized and broken down and it finally moves off. Remember that your rocuronium and vecuronium, all of your non-depolarizing muscle relaxants, they bind in a competitive way to the nicotinic receptor. So when it comes to reversing the muscle relaxant, only your non-depolarizers can be reversed. We give neostigmine that is going to increase the amount of acetylcholine esterase. It's going to block acetylcholine esterase, which means that your acetylcholine that is continuously still being secreted does not get broken down. So when you then have more acetylcholine in the neuromuscular junction, they become like the bullies in the playground, and there's now more of them, and they tell the little rocuronium, get out of my lock, leave my lock, I want to get into my lock. And the little rocuronium says, oh, okay, and he moves away. Okay, so only your non-depolarizing muscle relaxants can be reversed, and we reverse it by giving something like neostigmine that blocks our acetylcholine esterase to allow there to be more acetylcholine so that they can move the rocuronium away from the lock. Okay, good. So I hope that makes sense, the difference between depolarizing and non-depolarizing muscle relaxants. Now let's come to malignant hyperthermia. So we're still talking about a neuromuscular junction. All right. And the important thing to remember is that with malignant hyperthermia, it's a genetic condition. So there's a genetic abnormality for Ryan, the friendly ryanodine receptor. Okay. So there's a genetic abnormality for the ryanodine receptor on the sarcoplasmic reticulum. There are other abnormalities as well, and it's not all related to the ryanodine receptor, but that is the most common cause that we found so far. So that's what we're going to focus on today. So when you get your normal nerve stimulation, acetylcholine is released, you get the wave of depolarization, you get calcium release, calcium binds to the troponin on tropomyosin, tropomyosin moves out of the way, and actin and myosin can kiss and be together. Okay, and then after a little while, Ryan, the friendly ryanodine receptor, will call the calciums back into the sarcoplasmic reticulum, and the muscle can relax. Now, with any of our pharmacogenetic conditions, you've got a genetic predisposition, but you need a particular trigger to set off the abnormality. So we need some pharmacological trigger that is going to change Ryan, the friendly ryanodine receptor, into, we'll call him Rhino, the very angry ryanodine receptor. Okay? And what are the triggers? What are the pharmacological triggers? And it is suxamethonium, as well as all of your volatile anesthetics. We see it most with halothane, but it can happen with any of the other volatiles. None of them are considered safe. So if you have somebody who has malignant hyperthermia and you know this, you cannot give them suxamethonium and you cannot give them any of the volatile anesthetics. You've got to give them a total intravenous anesthetic. Okay. So what happens? So we've now given Sux to the patient, and we know that Sux is going to, just excuse my cat who's meowing in the background. He's being quite persistent. So Sux is binding to our nicotinic receptor, and we get sodium coming in, and we get that depolarizing wave spreading all the way along. And we get our calcium, voltage-gated calcium channels opening, more calcium is released. You get that initial fasciculation or contraction, but of course then you don't close the pore, so you never repolarize. You just stay in a kind of limbo state. So what should happen is that after that initial fasciculation, the calcium should move back into the sarcoplasmic reticulum. But in this case, Rhino, the very angry Ryanodine Receptor, when he lets the calciums go, he tells them, "Fine, go, but don't you dare come back." So the calciums can't go back into the sarcoplasmic reticulum. So they are quite happy to remain chatting and playing with troponin on the trypamycin. And of course, actin and myosin are very happy because now they get to just be together and to kiss and to contract. Wonderful! Except, what is going to happen if you now have this sustained muscle contraction? It's a very rough bicep contraction, okay? So you now have a sustained contraction. You're basically doing a lot of exercise, right? So if you do exercise, what do we need? We need more oxygen consumption. What's going to happen next? You're going to produce a lot more CO2. So your CO2 production is going to go up. How does the body cope with this? The body copes with this by increasing the heart rate. So now you see a tachycardia on the monitor. You may initially see an increase in blood pressure as well. Okay? After a while, you're going to see that your CO2 levels increase. So on your capnograph, initially everything was fine, but slowly you're going to see that your end-tidal CO2 starts to increase in a stepwise fashion. Next, you're going to see that your soda lime becomes exhausted very quickly. And then your inspiratory, your FI CO2 also starts to go up, right? And then you're going to start to see an increase in the temperature because you're doing sustained exercise. Every muscle in the body is contracting, isn't that right? So you get tachycardia, you get an increase in your CO2 production, you get an increase in oxygen consumption, and eventually you're going to end up with an increase in your temperature as well. But that's not the first thing that happens. Okay. And is this sustainable? No, it's not. Eventually, you're going to run out of resources, you're going to build up too much toxins, and the patient is going to die. Unless we can give them something called dantrolene. Now, dantrolene is interesting. It is actually a skeletal muscle relaxant. It wasn't very good in clinical practice because it didn't really paralyze any of the smooth muscles in the gut. So it didn't make our abdominal operations any easier. But it works specifically on this calcium mechanism in terms of muscle contraction. So giving dantrolene is the only thing that can reverse this whole process and can get the calcium off the troponin. And then you can get muscle relaxation again. But it's important that you look up what the dosage of dantrolene is, and it's important to know how to mix it because it's not an easy thing to mix and you need a lot of it, especially of the old traditional kind of dantrolene. So if you see this kind of picture, then you need to call for help. You need to start cooling the patient down by whichever means possible. You must give more oxygen. You must get rid of the CO2. And then you must get your stock of dantrolene as quickly as possible. Okay. But that basically sums up what happens in the neuromuscular junction. We've spoken a little bit about the excitation-contraction coupling that happens, as well as the function of our muscle relaxants, the two different groups that we get, and then we tied that in with malignant hyperthermia very quickly. So I hope that this makes sense to you. If anybody would like to have a little bit more information, these are the references for the talk. This YouTube video in particular, the crash course video, is very nice if you just want to recap how the muscle physiology works. And then the other two books are more just the academic background for this. So I hope this was helpful. I'll see you again next time.